Hey everybody, welcome back. This is Middle School Math with Dr. Koenig, and today we are continuing our study of systems of equations. This time we're learning to solve using substitution. It's a different method than the graphing method we used before, but I think you'll like it. It's algebraic, it's methodical, you can kind of follow some really substantial steps to solve your system. Let's jump in. Here's our first example of a system of equations. You'll see that I have, again, two equations, and I'm looking for the solution. Now remember when we covered graphing, the solution was where those two lines meet. So we're trying to algebraically figure out where these two lines meet. Now, in this example, I'm going to do that using substitution, which is an algebraic method. So I'm going to take this 2x, which I can see is equal to y, and I'm going to replace in the other equation y with the 2x. I'm allowed to do that because I can see in my first equation that 2x is in fact equal to y. That means they're the same thing. I could say 2x or I could say y, and I would be talking about the same value. Now, when I plug it in, it looks like this. I've got a 2x on the left side. That's my substitution step. On the right side, I still have my negative 3x minus 15. This gives me an equation that I can algebraically solve. So first I need to get my x's together, which means I need to move this one to the left-hand side. Remember, when you're solving something algebraically, you can't just move it, you can't change where the equal sign is, but you can manipulate it algebraically. So it's a negative 3x. I could use a positive 3x as long as I do the same thing on the left side as I do to the right side. On the left side, I get 5x, and on the right side, negative 3x plus 3x leaves me with 0 x's, so I'll just bring down my negative 15. From here, I can divide by 5, which means I now know that x equals negative 3. Now that's great information, but it's not the final solution. Remember, the solution to a system is the coordinate, the point, where the two lines meet. And a point, a coordinate, has an x and a y, so I still need to know what y equals. I'm going to go back to my original equation where I knew that y was equal to 2x or 2 times x. I now know what x equals, so I can plug that negative 3 that I just found in for x. This is another form of substitution. I'm just saying that I know x is negative 3, so I can replace x with negative 3. That gives me two numbers I can multiply to determine that y is equal to negative 6. Now that I have an x and a y, I know the solution to this system. Remember, the solution is a set of coordinates, an x and a y, in that order. So negative 3, negative 6 is the solution to this system. Let's try another one. Here's another example. In this one, I'm noticing that I have x isolated, and that's an important step. I didn't really talk about it in the first example, but it's important to recognize whether or not you have a variable isolated. In this case, I have x isolated, which means that I know what x equals. X equals negative 5y plus 15. So I can take that negative 5y plus 15 and I can plug it in instead of x in my second equation. Now, when I do that, it's going to be really important to use parentheses just like I'm doing here. That helps me keep the entire x value together because in this equation, I know that I need to multiply 3 by the entire x value. I'll still bring over my minus 4y and my equals 7, and now I've got a whole equation I can solve. So my first step is going to be to distribute that 3. Remember that if there's a number outside the parentheses, that means it needs to be multiplied by everything inside the parentheses, but not the 4y because it's not in the parentheses. From there, I can see that I've got some like terms. So negative 15y minus 4y would give me negative 19y. I'll bring down my plus 45 and my equals 7. I know that my next step is to subtract 45. On the left side, I still have negative 19y. On the right-hand side, I have negative 38. The last step to isolate y is to get rid of that negative 19, so I'll divide it on both sides, which tells me that y is equal to positive 2. But remember, just because I know one coordinate doesn't mean I have the final answer. I need to take that y value and plug it in somewhere. I'm going to do that in the original equation because x is already isolated, which means plugging in y should be relatively easy. x equals negative 5 times y, and I now know that y is 2, so I'll plug that in, which means that x is equal to negative 10 plus 15, or x is equal to 5. Once I've got both pieces, I now know the solution to my system. The coordinates to the solution are 5, 2. Now, in the last video, we talked about how there are special solutions. Many systems have one solution. They have a point where the two lines meet. That's great. But we learned that sometimes lines don't have any points where they meet, and sometimes they meet in every single point. They completely overlap. So let's look at what that looks like when you're solving algebraically. I'm still going to use substitution. I see that my y is isolated, which is an important thing to notice when you're getting started. That tells me that y is equal to 2x plus 3, so I can plug in 2x plus 3 for y. When I do, I get 4 parentheses 2x plus 3 equal to 8x minus 36. Remember, when you plug in something to use parentheses, that just helps you make sure that you're multiplying 4 by everything inside those parentheses and nothing's getting missed. Now, I will distribute the 4 to give me 8x plus 12 equal to 8x minus 36. And I see that I have x's on both sides of my equation, and just like last time, I need to move one of them over. I usually move them over to the left, not because that's any more right or any better than any other way. It's just the way my brain works, I guess. So I will subtract 8x, but whatever I do to one side, I have to do to the other. Now look what happened. I have no x's left on the left-hand side. In fact, I have no x's left on the right-hand side. But this says that negative 12 is equal to negative 36, which is not true. When you get a not true solution, or a not true equation, essentially, I get two things that are not equal, that means that this system has no solution. Remember, if we were to graph something that had no solution, that would tell us that these are two parallel lines. They might look something like this. And what we know about parallel lines is that they have the same slope. That's why they never meet. They're rising at exactly the same rate. They'll never meet. They don't have any points in common. So this is a no solution problem. Your clue for that is when you get something that is false. 12 does not equal negative 36, so this system has no solution. Now, you might remember from the graphing lesson or from any graphing lesson you've approached that there are 3 solution types. Some systems have one solution, that's a point where those two lines meet. Some systems have no solutions, that means you've got 2 parallel lines like the last example we looked at. And some have infinitely many solutions. So, spoiler alert, we're about to look at one that has infinitely many solutions because it's important to know how to recognize the difference between no solutions and infinitely many solutions. So, here you'll see that y is isolated. That's great. That means I can plug in all the stuff behind it, 2x plus 3, in place of y. Now, we haven't addressed any where a letter wasn't already isolated, but I do want you to notice that in this system, in this method of solving, you need to have a letter isolated. So if you get an example where, let's say you had 3y is equal to 12x minus, 6, you might have to do some work to isolate that variable before you can then plug in or use the substitution method. So that's something important to point out here. Continuing with this example, I now have 6x minus 3, and then again, be careful that you're using parentheses because when you substitute something in, you need to make sure that the entire thing is, in this case, being multiplied by that 3 when we distribute. So I used my parentheses, it's equal to negative 9. Let's go ahead and distribute, and remember that what I'm distributing is a negative 3, so I'll get negative 6x and I'll get negative 9 or minus 9. And what I notice when I go to solve is that I've got some terms, some like terms that I can combine, but 6x minus 6x is 0x. So I'm left with negative 9 equal to negative 9. Now this is different from the last example where I got 2 things that were not equal. In this case, I got 2 things that are equal, and that tells me that this is an example of having infinitely many solutions. If I were to graph these two lines, what would happen is I would graph the first line. It's something like that. And then when I isolated y and graphed the second line, I would find that they're actually the exact same line, which means that they have infinitely many solutions because every point on one line is also on the other line. So they have infinite points in common, therefore infinitely many solutions. Now your key for this is that you get two things that are equal, but all of your variables were canceled out. On the last example, when there was no solution, you got two things that were not equal. So substitution requires you to replace a variable with something equivalent to it. It's important to do that when a variable is already isolated. So you might have y equal to 2x plus 3. It really doesn't matter what the other equation is. That one could be in standard form. It could be 4x minus 2y equal to 12. It could be any kind of form, in fact, but when we have one variable isolated somewhere, that tells us that we can plug all that information into the other equation and start solving algebraically. So this is one of 3 methods, so this is the second video I've posted. I'm going to link the other 2 here, so you'll have a video on solving systems by graphing and another video on solving systems by elimination. If you're looking for help in those areas, feel free to check those out. Otherwise, go solve your systems and have a great day. I'll see you next time.